Hi, I'm Abdulmumin Usman. Uh, I'm also known as Balogun. I'm a software engineer, currently engineering manager at RiseVest. So, quick plug for those who do not know RiseVest. RiseVest connects users to the best wealth creating opportunities in the world, either through our managed service, which is known as RiseVest, right? Or our investment service, ISA, um, and also our alternate markets for private investment, known as asset base. Um, so I'll just be taking us on a journey of how we um, rebuilt Rise Vest, the core Rise, based on users.
Hi, Abdomen. You're not sharing your slide.
Okay, can you
Yeah.
see my slide?
Yeah, we can see it now.
Yeah. Alrighty. Let me
Can put it in the slideshow.
just a moment. Okay. All right. So quick introduction. I've done that, but let's just get like the backstory of this. So when we set out to build Rise 3.0, it was a refresh of the UI, but not just the UI. There were some pain points, especially with the UX, how the users interacted with the app. Essentially, um, it's more about an empathetic way of just stepping into the user's shoes and trying to solve for that problem. So just take us on the journey of um, how this surfaced from like a user problem, how it was implemented, breaking the chain, then closing the loop. So we're going to take a journey from like the client, go to the server, then back to the client. Then we would discuss like roads not taking, like alternatives. All right. So it all starts with the user. Um, so typical experience when a user is trying to um, carry out an action that involves interactions with external systems, for example, like third-party systems. So you just tap, you wait, you refresh, you wait again, and queue the app, then reopen. Um, why would this happen? Um, just a simple user journey. So the user tries to fund, right? This request gets to like a server, um, and the server does whatever validation it needs to do. Then it fires that request to like a third party. Let's say the third party takes a while to respond. Um, and in the middle of this, the request just times out, but the customer gets debited, and the UI state doesn't actually reflect that. So this just leaves like the customer confused because there's like a discrepancy. Um, yes, I wanted to fund, I was debited, but the UI, which is the client, which the customer is using, does not reflect that state. So the customer has to do what he has to like refresh um, manually. This is not UX. Why this seems like a negligible UX. It's not the UX we were gunning for, right? Um, and there were other things that we used to try or used to do, which is you could you could do some optimistic updates on the UI itself, right? Um, so immediately but optimistic updates only make sense when you know that okay, the request has gone and you got like a success response or something. Um, we also tried like polling, right? You could do polling. You could just poll at intervals, maybe 30 seconds, whatever um, interval that you settle on. Then the other thing, um, which you could do, is to trigger a refresh using heuristics. So heuristics in this case are like app heuristics, like the app state or the life cycle of the client. So I'm using a mobile client as an example. So heuristics you could use the user closes the app, not close the app, just minimize the app. Maybe they go back to another app, maybe some app like Twitter or WhatsApp. Then they come back to the app, right? You can use that as an indication to okay, let me refresh at this point. Or the user blurs out that screen, right? Maybe goes to another screen within your app and comes back to that screen. You can also use that heuristic to say, okay, yeah, let me just trigger that refresh again. Um, but that's not well, it's heuristics, it's not deterministic. Have it doesn't truly state what is actually happening on the server, right? So let's just go through what actually happened on the server. Um, so the old way, which is just a typical request response cycle. So the server receives a request, for example, a post request to API/fund. It does any needed validation, right? And make some intermediate calls, so maybe like some internal service. Then calls like the third party provider, then waits on the provider for a response before returning that response to the client. Right? You can see it's a chain of action from validation to calling the third party to maybe like transforming your results before you then return it to the client. Um, so the problem with this approach is the problem with this change approach is you have like a synchronous communication between like your services and the third party. So, for example, the internal services could be communicating over REST, and you are essentially waiting on that result before you proceed to the next thing. Same thing with the third party. You're making a request, you're waiting on that request before you proceed to the next thing. So you have a situation where your request is coupled, right? It's coupled to um, those other services. So your request is essentially coupled in space and time. Um, it's coupled in space such that one service has to know how to find the other service, right, to be able to talk to them. Um, Also coupled in time because, yeah, both services have to be available. If not, the request is going to fail. Um, it's also coupled along like latency because imagine the third party. Uh, im- Imagine the third party takes 30 seconds and you have like a timeout of like 20 seconds. You don't want the user to wait forever. Um, you are essentially coupling like latency as well because the entire life cycle latency is a sum of all downstream latencies. So the latency of the services themselves, the latency of like the third party which you do not control. um, then what happens if like the request is received but by the third party, but then it just times out um, in between or so. So that's the chain of requests. So how about we just break this chain? Do we have to wait for everything? Um, so what if we stopped waiting? What if we just let the users get a feedback immediately while we update them on the status of their request? So the problem with the initial approach, as we discussed, is it's coupled. So you both systems have to be up and running. So it's coupled to the other systems uptime and latency. So which makes it synchronous. So what if we could make this like asynchronous instead? How do we go about it? So one way we could go about it is just having a system of passing messages, right? So we have a system where um, an initiator or a caller registers an intent without waiting. Like it just registers the intent and bounce, right? And the callee just the responsibility of the callee is just to also report back to the caller about what has happened. So we can achieve this by just passing messages between the caller and callee. That's like a an abstraction, an abstracted way to look at it. But caller and callee in this case are just systems. Your system, third party system, or whatever. So messages are like a generalized term. For our use case, we'll be looking at two types of messages. We're looking at commands and events. So what are commands? Commands are just messages that express intent. Do something. I want you to do something. Just do this at this point in time. So it's directed. So you have like one recipient, for example, and it must be processed exactly once. It can fail, and maybe you want to retry it. And once the recipient or consumer um, does get that message, there's also the consumer also has to like acknowledge. And you can also have like priorities with this. So you could have like urgent. You could structure it in such a way where you have priority queues and all of that. So for this, we used like RabbitMQ um, to just give to just enqueue commands, right? So RabbitMQ, you could just have like a worker that just consumes from a queue and essentially processes the work in the background, right? You could have priority queues, urgent first, dead letter queues after like maximum number of retries. It just goes into the DLQ. Then acknowledgement, which is you have like a guaranteed processing. Um, then for the events part of the messaging, events are just facts. They express something that has happened. Um, so, and generally events are just broadcast. You have many listeners, maybe like a producer, different consumers. So you could have multiple services just react to that event simultaneously, independently. Um, so you could generally, with an event system, you could just use something like a simple pop sub uh, system. So, and would get into that. We actually use NATs, and NATs by itself is a simple pop sub system, like fire and forget system. There is no persistence, or there's no capability of you replaying an event. For example, if a service is down and it wants to start consuming from a certain offset or so, With NAT, generally, you cannot do that. But NAT also has the integration for you to do that, which is called JetStream. So you use NAT with JetStream. So NAT JetStream. So NAT JetStream, it gives you the same, pops up multiple subscribers, like one, as many producers as you want. It's fast, usually sub millisecond latency, and it has like just simple operation. You don't have to deal with partition management as opposed to when you're doing using something like Kafka. Then you can also replay stream, right? Which is the just stream part of NAT that I mentioned. That's just the persistence layer on top of NAT. So NAT is just NAT was built for um, low latency pub sub system. That's what it was built for. But you could add JetStream on top of that to for the persistence, just as you would have with something like Kafka. So for the life cycle that we saw, the simple life cycle we saw, if we do use the messages as we have defined them, and which is how we currently do them, right? Um, the server just receives the request, validates the request, then it enqueues a command, right? And it just returns 202 to the client, which is accepted, like that request was accepted. But it doesn't mean that the request is done, just accepted. It's processing somewhere in the background. And you have like a worker just consume the queue, and within the worker, that's where you call like your third party provider, and do any other intermediate calls that you need to do. Then when you get that result, you can then broadcast. Um, you can broadcast an event. For example, the journey we've been going with so far has been a wallet funding scenario. So you just broadcast an event, wallet funded. It happened. It's a fact. Um, so um, now, if we do this by us, we breaking this chain, right? It's not. It makes the client. You put the client in this scenario where in a spot where, okay, you are returning to the client immediately. So then what's happening? Like, as the client, how do I know that that request is actually even going? What's up with my funding request, for example, right? So, which brings us to closing the loop um, of this entire journey. Um, so, back to the user, we started the journey from the user um, trying to fund, which was speaking to like a third party service, but something happened in between, and there's a mismatch between like the UI state and what actually has happened on the server. So your funding is processing, but now what? So how does the user know when it actually completes? Like, what if the third party rejects it? What if the app is closed? What if there's no internet? Like, how do I know? I just clicked on funding and it went immediately, and what's going on? So we made the server async. So it's now the time for the client to also participate in this entire structure. So we also, going back to our solution for having things async, we mentioned that we needed a way to pass message, right? So we also need a way to send messages to the clients from the server on the status of their requests, right? So it's the server is processing it and the worker, fine. Okay. What if it fails, how does the client know? You have to send message. You have to send a message to the client. But first off, we have to first look at how does the client fetch data and like display the data. So the client just has like a query engine, right? That queries the server. Then your response is usually is cached, right? In memory or using like a persistent storage. So there's um, what is actually used here is a memory mapped storage for mobiles. So, for example, on the mobile side, it's a memory mapped storage, MMKV, um, which we could also go into that one separately. But so this cached persisted data is actually what is displayed to the user. So we've seen through this loop that, okay, the client needs to make a query, and that query is cached, and that's what the user sees. So what this means is that we need a way to tell the client, to inform the client that something has happened, right? Just the query engine should just refetch a particular data we know has indeed changed, right? Um, So for this, there are different solutions which would explore as well. But going through the happy path of our journey. Um, so for this, we use FCM, data only messages, to send the message from the server to the client, like a one-way connection. So FCM also gives us like best effort delivery. The messages are queued and retried till they deliver. They also work in both queued and background states. So whether you like remove your app from like the minimize tree, or you are on Twitter, it also delivers. It works. It also works on poor connection, on poor networks. Um, the downside to FCM is there is a limit to the size of message that you can send. So the limit is 4 kilobytes. So you have a 4 kilobytes limit of message that you can send across. Um, but for our use case, we just need a signal like an event type or with some metadata, maybe like an ID. So we theoretically would not meet that limit. So generally, this is the difference between if you've used FCM, that is Firebase Cloud. A normal FCM message is just the notification field. So FCM push messages have like a notification field, which signals to FCM that, okay, this is a notification, maybe pop up the notification overhead as well. But with a data only message, you're only sending data to the device, and the device can decide how it wants to handle it. So this also uses the same. So we also use FCM for push notifications. So it also uses the same setup of how we do push notification, which is each user has like a topic, right? And no matter, let's say user has like 3 clients, you could just have a group key under that topic, right? And when a message is posted to that topic, it just fans it out to like those group keys. Um, so roads not taken. That's essentially like this is essentially what completes like the loop of um, telling the client when to refetch, right? Um, so you have like this system where um, something happens, wallet funds, the user doesn't even need to do anything. They just see it. It's near real time, not as real time, or but near real time. Like for this use cases, it's sufficient. So roads not taken, which is essentially YX and not Y. Uh, so yeah, Kafka, which is the default, would I say, in the industry when it comes to like events. Um, so why NATS and not Kafka, right? So Kafka does boast of like high throughput, like if you have large volume of events, Kafka is definitely the one you want to go with, right? And it is poised as an event logging system, right? That's as at its core. While NATS is just like a low latency pops up system, then you can bolt on anything you need on top of it, right? Um, so another reason why NATS and not Kafka is like easy deployment, because we for our NATS we manage like the deployment ourselves, right? It's not like we don't use like a managed service. It's deployed um, like internally. Um, for Kafka, you generally have like a um, deployment is generally like complex, and in older versions, was it? I think it's less than three or so. You also need like Zookeeper, which is another like another component for Kafka to be able to run, right? To the like the deployment point as well. The deployment as well. NAT is just simple. Like it's simple and lightweight. It's literally just a single binary um, of about 20 megabytes, 20-ish megabytes, um, and you are up and running with the single binary. You can use NAT bare bones, which is the fire forget um, low latency pops up. You can also use you could also use it with stream. Um, Whereas for Kafka, it's more of like a multi-component system. And in recent versions, you don't really need Zookeeper, because there's Kafka Raft as well, which Kraft, which serves the same purpose for metadata and all of that. Then another thing that really stands out is the routing efficiency for NAT. So NAT has this thing called like subject-based addressing, where you could, as opposed to like topics for Kafka, where you have to create like a topic for each event. But with NAT, you have like this hierarchical um, hierarchical thing called subjects, and with the subject, you could essentially um, target. You could be granular with your event, and the consumer essentially through the NAT protocol, you could say you just want to listen for a range of events. It's flexible. It's an ergonomic thing that just improves like DX, to be fair. And the protocol, the NATS protocol itself, it just handles it as a string. So it's a string with a limit of 255 characters. So you just have like dot separated subjects. Um, yeah, and you can listen for the stream using like complex, like you could use wildcard patterns to just listen for different streams. You just have like this efficient way to only listen for this thing or that thing. I can see my time is fast spent, but I'll just go do this as well. So the other thing for the clients is why FCM and not something like WebSocket. So uh, for our use case in the journey that we went through, we'll see that what we needed was you just something unidirectional, just one direction from the server to the client, and that's what SSC can give you, right? Um, WebSockets are bi-directional, but one way FCM stands out because from the standpoint, if you go back to our point on that, you'd see that um, we are really concerned about simplicity and resource, right? So FCM also has a shared a persistent network, which is used like system wide. So every app it uses just one persistent network, which is just demultiplexed into like based on like your app bundle ID. So just one connection, then it just routes it to wherever it's coming from, as opposed to SSC and WebSockets, which is managed by each app process, right? And what this means is that you are using more battery, right? Um, you're actually using more battery. The for and we don't actually, it's not something that is frequent, so we don't want to keep like a connection that is just alive for and drain the user's battery um, for that use case. Um, so I'll just quickly, I think I have 2 minutes, so let me just go to, I think we're at the end. So one, a good deal of the learning around like um, the decisions and everything, yeah, we did for this entire flow is actually summarized by this tweet. So in system design, we always mention scalability, and most times we do not consider like efficient use of resource as much. So efficient use of resource, simplicity, and scalability, of course, were at the forefront of the design choices that um, for this. And just drilling into it that deeper, you just get to um, from the user's point of view. Let's say you're respecting the user's resource, for example, the battery and um, all of that. It makes you just reflect on, okay, on your design choices. So I'll say the greatest the learning, the key learning here is whenever we are thinking about system design, aside scalability, maybe you should also think about resource use. Yeah, so thank you. You can find me online. I am Balogun of Africa almost everywhere. um, yeah.
All right. Thank you so much, Abdulmamir. You actually have three questions, but I'm not sure we have the time to attend to these questions. So maybe we'll just collate these questions and then send to you um, after
Uh,
these sessions.
Sorry to interrupt. I think we can try and take one or two.
Okay,
Okay.
let's go. All right, so we have the first question here from Daniel Kurunku, who is asking, but the asynchronous pattern, will it not be an overkill for non-mutating requests? For example, get requests that should fetch a user's balance or profile.
Yes, it's not. So it's the asynchronous pattern is not used everywhere. Like you for the use case you mentioned just now, you need the data immediately. So you still have to like use REST, communicate over REST for that, grab that data and display to the user.
Okay, so I guess I can still ask the next question. Does not maintain a schema registry? This is from Justin Rabo.
Does not maintain a schema.
Maintain a schema registry.
Mm, So by schema, if just to, I want to clarify on that question on what they mean by schema registry. So
Okay. So Justin, please, maybe you can just clarify what you mean by schema registry. I think the next is, do you use FCM for both commands and events? If yes, is there any level of fault tolerance or no need? This is from an anonymous person.
okay, sorry, I think I was checking the wrong place. Do you use FCM for both commands and events? If yes, so FCM is mostly used just for the client, and it's more about it's an event, not command. It's just something has happened. Just refresh yourself. Um, the balance has updated. Refresh to get the new balance. Or you created a new plan. It was processed in the background. It is already there. Just refresh to see it there. So
Okay.
it's events, not commands.
Okay. Okay, so the last question is, this person says, I must have missed the conclusion for the keeping the client up to date. Are things like balance or important states managed using SSC or WebSockets?
Yeah, they are managed using FCM, data only messages that are posted from the server to the clients. So, and that was why we also went through the last part where we went through, which is why FCM data only messages as opposed to WebSockets or server sent events. So it's
All right.
essentially it is FCM data only messages. Yeah.
Awesome. Thank you so much once again, Abdulmumin, and thank you everyone for joining.